All right, we're going to talk about two-source interference, in particular for sound waves, but the same concept applies for two-source interference in optics as well. So in this case, I've done a demonstration for you as well, and then we'll talk about the limitations of the demonstration afterwards. So let's just say that we have two sources, source 1 and source 2. And for right now, let's assume these sources are emitting isotropically, spherically, the same in all directions. So you can see what I did here. Comp here means compression. So what I did is I just took this ruler and just kind of sweeped it and made these arcs. That's how I made that, put the marker on there. And anyways, what we see here is there are certain spots where both waves are at a compression. You can think of that as this wavefront here being the compressions. So for example, right here, both of the waves are at a compression, which is an overpressure maximum. So that's a spot where both waves should constructively interfere. Same right here. What about right here? This wave, it's about halfway between, that's a rarefaction for one wave and a rarefaction for the other one, right? It's a rarefaction for source 1, a rarefaction for source 2. At that point, it's also constructive interference because it'll be an overpressure minimum. Same right here, same right here. And you kind of see this pattern here. When you have two sources, we expect constructive interference everywhere on this line. But now what about this spot right here? In this spot, we see a crest of a wave, I should be careful, a overpressure maximum or a compression here, but a rarefaction from the other one. Those two should tend to cancel out. Same right here, same right here, different spots. And so there are going to be spots where there's cancellation or destructive interference. So I should probably put that up here too. So the question is there a general way we could talk about this? There is. Let's pick an arbitrary point here. How about just right here? We'll call this the point P. All right? There's going to be some distance from source 1. You know what? I'm going to do this in black just so it shows up. I'll call that ray 1 or distance 1. There's also some distance here. We'll call that R2, distance 2. Now, in general, we don't know which one's going to be longer, but the path length difference should equal R2 minus R1, and if you want, you could slap an absolute value on that. All right? So that way, if for some reason, if we were down on this part of the graph, right, R1 would be longer, and you'd still get a positive path length difference. So when are we going to see constructive and destructive interference? I think I'm going to need a little bit more room here. So let's put this up higher. Sorry about that. So the conditions, there's a bunch of different ways we could say this, but the way I like to think about it is if delta R is equal to an even number of lambda over 2's, or you could think about it as an integer times the wavelength. So a lot of times I talk in terms of lambda over 2's, and you'll see why here in just a second. Get this a little higher in a minute. So for constructive interference, think about this. If the path length is exactly 0, if the integer is 0, there's no difference. The sound waves travel the same distance, and you get an overpressure maximum for both, or an overpressure minimum for both, etc. Now, what if you travel one extra wavelength? So let's say this path R2 was exactly one wavelength longer. Well, in that case, you're still going to get both of them at an overpressure maximum. Notice something here. We're ignoring attenuation. Absorption of the sound waves. Strictly speaking, we're also ignoring the fact that it just travels farther, so the intensity of this sound wave should be a little bit lower. But we do expect that at this point, there should be at least some constructive interference if this is an integer number of wavelengths. It might not exactly double the sound because the sound waves have to travel different distances, and we're ignoring attenuation, but it should be at least significantly louder. All right? What about destructive interference? Well, if delta R is equal to an odd number of lambda over 2s, and now you know why I brought up the lambda over 2s. So in this case, if you have an even number of lambda over 2s, you get constructive. If you have an odd number of lambda over 2s, you get destructive interference. Said another way, if you get an integer number of wavelengths, constructive. If you get a half integer number of wavelengths, which can only happen with odd numbers, you can't have 2 lambda over 2s, that gives you constructive. You have to have odd numbers here. Is there anything else I wanted to say about that? I guess we could mention the phase angle before we get to the example and the demonstration. The phase angle okay, it looks like I might have a typo there. Looks like I do. I better fix that in the book. But good thing I've got it right on the board here. So in this case, if you want to get the phase angle between the two waves, you can do that. So if you're at some arbitrary point, you can calculate the path-length difference, and if it's not perfectly constructive or destructive interference, you could figure out the phase angle and use a phase angle to relate these two waves. Collinearity. I mentioned this here just strictly because the sound waves are not traveling perfectly collinear. There's an interference pattern that shows up associated with sound waves traveling in an angle, and it's pretty complicated. It's beyond the scope of this course, so we're just going to assume collinearity. So we're going to assume that these waves are all traveling the same way, and obviously that's approximately true here, but if they were at right angles, that wouldn't necessarily be true. Now let's get into the demonstration, and let me phrase it here. Let's go over to here. All right? So imagine we have two sources separated by 2 meters, and there's going to be 2 points that we want to put the microphone, point A or point B. Okay? And notice both of these points are about 3 meters out. Because I call this the midline sometimes. I don't know if anybody else does. You could call it the perpendicular bisector through the midpoint between points 1 and 2, but that's kind of long. I just call it the midline. So, right, you can see that this showed up in the last problem, so I just drew that, and that's how I usually draw a 2-source interference problem. I usually draw this perpendicular setup. Okay, we want to find the lowest frequency which causes destructive interference, and then what happens if we use that, and all these questions. If you want to pause the video and try it yourself, this is the time to do it. If you don't want to try it yourself, well, that's fine. And maybe just to give you a visual on this, let's do this. Okay. So I've got some marks here on the ground just to help me set this up. And then we can run the experiment afterwards. So I've got to be a little bit careful with this. I know my picture is backwards. Sorry, I always do that because I'm on the opposite side. But so I have speaker 1, speaker 2. That's a 2-meter stick on top. This green piece of tape is 3 meters right here. So this would be point B, and this would be point A. And then we've got sources 1 and 2. So this would be source 1, it's basically right here next to this. And just, oh, I do have some meter sticks here I could show you. Here's 3 meters, just so you got it for reference. Pretty darn close to 3 meters, and hopefully this is perpendicular. It's pretty close to perpendicular. All right, so let's get to the board work, and then we'll do the simulation. Or sorry, the demonstration. So let's go back to the board too. That helps you. So if you're wondering what the source 1 and source 2 are, think of them as the speakers. All right. What is the lowest frequency causing destructive interference? How are we going to approach that one? So for part A, we want destructive lambda or delta R has to equal an odd number of lambda over 2's. All right, so in this case, we want the lowest frequency. So let's think. C equals F lambda, where C is V sound, just so I don't have to write as much. And so in this case, I want a low frequency. How does frequency relate? Frequency is C over lambda. If I have a long wavelength, I will get a low frequency. So I want the longest wavelength. Well, let's look at what lambda is. Lambda is 2 delta R over an odd number. Well, if I want lambda to be as big as possible, to make the frequency as low as possible, I want to use a small odd number. The smallest odd number is 1. Okay, so now all I need to do is figure out that path length difference. Well, ray 1 in this problem is 3 meters. Take a second to figure out what ray 2 is. If you want to pause the video and do it yourself from here, see if you can beat me. I'm going to proceed in 3, 2, 1, okay. There is ray 2. I think I switched the colors, but oh well. Oh no, I did it. Okay. This is 3. This is 2. R2 should equal the square root of 3 squared plus 2 squared. And then just to speed this up, I did the math. I think it's 3.6055 meters. Obviously, we don't need all those digits. I'll explain. Let me make sure that I wrote that down right. Okay. So one reason we might want to keep extra digits is we're about to do a subtraction. So you might be saying, dude, you only need 3 sig figs on your final answer. Why not just keep 4? Well, if I do a subtraction, this one from that one, I'm going to lose a sig fig and I'll be, right? I want to have an extra digit so that I don't have intermediate rounding. So because I'm doing a subtraction of 2 numbers that are kind of close together, I'm going to keep the extra digit in this case. Obviously, you could use stored values in your calculator, and that's a nice way to do it, or use an Excel spreadsheet, which does the same thing. But after this, if you do the math on this, lambda equals, delta R would be 0.6055. So lambda ends up being 1.211 meters. I think something like that. All right. So then if we plug that into this relationship, F ends up being, oh, I forgot to mention, unless otherwise specified, we usually assume V sound equals C equals 343 meters per second. Sorry about that. I left that piece of information out. I think somewhere in the workbook I mentioned this, but that's kind of your default sound speed. That's room temperature. We know that's close even if the temperature's off. All right, so out of all that, what did I get? 283, I think. All right. So we've got part B and B star here. Let's leave B star till the end. If we use that frequency, this frequency is the lowest one, which should cause destructive interference. But when I use this at point B, will we expect constructive or destructive interference? Pause the video. Again, if we use F from part A, so if we use 283 hertz, the frequency that causes destructive interference at point A, if we use that frequency, but we place the mic over here at point B, do you expect constructive or destructive interference? I'll answer in 3, 2, 1. We expect constructive interference, right? Why? Because the path length difference should be the same on the midline. Or sorry, the path length difference should be 0 on the midline. The path lengths 1 and 2 are the same. The path length difference is 0. I misspoke. Okay, we'll come back to B star at the end. What is the lowest frequency giving constructive interference at A? And you can try and do both C and D right now by yourself. I'll go ahead and put the answers up. Let's see. Delta, so if you want to pause the video, this is your last chance. 1, 2, 3, here I go. R equals 0.6055 meters, I think we said. Somewhere in there. I think it's actually off here, right? But we'll keep the extra digit. And so if delta R is equal to lambda, we'll get constructive interference. 2 lambda over 2's, or lambda. So an even number of lambda over 2's. So in this case, now you might be saying, why don't you use 0? Well, we can't have a path length difference of 0 at point A. Right? So the path length difference has to be some non-zero quantity. That's why I use 2 as the lowest even number. And so out of all this, you should find that the wavelength is half as big, which means the frequency is twice as big, which gives you F constructive is, what is that, 5 something? I don't want to screw it up. I'm very tired. What did I write that? 566. Let's make sure this gets on the screen. It's there, 566 hertz. Okay. And then part D, if you want the second lowest frequency giving destructive interference at point A. Notice all the crap we have to specify. Which frequency, what type of interference, and where is it located? It's like Clue, the Colonel Mustard in the conservatory with a candlestick. Oh my gosh. Does anyone even play Clue? I don't think so. Tim Curry, mad props. All right. I don't know. What was I doing? Let's just look at this answer right here. This frequency was the lowest. Now, if we change this odd number to 3, right, that's going to, how will that propagate through? Instead of using 1 here, we would use a 3. So that would divide the wavelength by 3, which would multiply this frequency by 3. So 3 times this frequency. And we can start to see a pattern here. So that would be, what is it, 850 or so. So we see that as you start to increase, well, I guess that's part E. What should happen to the sound intensity? Not sound intensity level beta, but sound intensity I at point A if we're going to sweep the frequency upwards. If we start at 200, as we increase the frequency, think we should hit a dead spot when the frequency hits 283, and then we should see it get a loud spot at 566, and then it'll go dead. Now again, because these speakers are not equidistant from the source, the sound level is never going to completely die out. This one has to travel through more air. There's more attenuation. It's farther away. This sound will be lower intensity at point A than source 1. So it's never going to completely cancel out. That's one of the issues here. So let's come back to B star after we run the experiment here. So let me turn this on and point it towards my, I guess I can do this. We'll go like this. Give me just a second. It's kind of tricky to, come on now. Why is this monitor not working? Did I pull the cable out? Oh my gosh, really? Okay, I guess, man. I guess we'll just get this demonstration over with. All right, always something, huh? Let's go 3 and zoom out. Sorry, give me a second. All right, then let's autofocus. There we go. All right, sorry this is such a crazy mess in here. All right, let me go ahead and turn the speakers on and we'll do this. All right, and I don't want to spend all day. Speaker 1, speaker 2, and I'll tell you, surprise, it's not going to work very well. All right, so what frequency did I set this at? 283. All right, and hopefully, one of the challenges I face is the microphone doesn't have a long enough cable to get over there. So I had an alternative setup ready to go with the sound sensor and the monitor, but the monitor just cut out, so we'll just kind of do this way. I'm just going to show you that if I tell you what I'm going to do. I'm going to shut up for once. I'll move the microphone around, and even though this isn't perfect, I want you to notice that the volume does change a little bit as I move this microphone around as much as I can. All right, so hopefully you notice some dead spots in there. Now, at B star, I said, what's going to happen? Right here, I have both red leads connected and both black leads connected. If I pull these leads out, now I only have one speaker connected. But what I could do is I could flip the polarity on this. And I could connect them black to red. And if I remember right, this doesn't work, but I'm going to just, yeah, so that ends up not working on this machine. So there's some polarity issue there, but in theory, maybe you've noticed that the speakers that you get, or if you've ever set up a home stereo system or some speakers, you'll notice there's cables where there's a, say a plain black cable and then a black cable with a white stripe on it, or a red and a black lead. And so if you flip the polarity of one speaker, what does that do? Well, that means this one goes from a cosine wave, so let's say this is a cosine wave and a cosine wave, and you flip the leads, this becomes a cosine wave and a negative cosine wave. That's the same thing as causing an extra lambda over 2 phase shift, right? So what that would do is everything on the midline should have destructive interference because the waves coming from here and the waves coming from there have the same path length difference, but we have an effective path length difference of lambda over 2 because that one's shifted. So that's what I was going to try and talk to you about on V. And finally, why does this stuff never work in the real world with this demo? Let's go over here to 2 and then move over. Give me a second. All right. Why does this experiment never really work? If you're in a classroom and some teachers try to show this to you, oh, whoops, there's that slinky again. All right, so speakers are not identical. They're not emitting spherically. There's attenuation, and I think I forgot the other one too. Different distances. Mean the two speakers will not have the same intensity at the same position. So there's a lot of different factors in real life. Like the sound waves can bounce off the wall or the ceiling or the desk or the other wall or the wall and then the other wall and then the other wall. And so if attenuation is negligible, so let's say we throw this one out because there's not a ton of attenuation over a few feet, right? But, or a few meters. There's still all kinds of issues here where we could be getting constructive interference from the whiteboard or the floor when we're not expecting it. And so that's one of the issues why if I try to set this up in the room, it still doesn't work. But I can tell you this, if you walk around, you do tend to hear a sound intensity maximum along the midline, and you usually do hear, your sound intensity maximum on the midline, and you do hear some regions where it's slightly louder and slightly quieter. Woo, that was a long one.